Scientists have made one of the most feared discoveries about the Yellowstone supervolcano. The volcanic caldera has been under strict observation for decades due to the danger that comes with the supervolcano's eruption, and now signs that it's about to erupt are beginning to manifest. This announcement of its eruption came forth after a rare gas that has been trapped in the Earth's crust for billions of years was detected around the volcano. What type of rare gas is this, and how is it a sign that indicates the Yellowstone supervolcano's eruption? Join us as we explore how helium-4 gas at Yellowstone's supervolcano indicates an imminent eruption. Located in the state of Wyoming is a national park which also has an active supervolcano beneath it. This volcano is named the Yellowstone caldera, with the power of its eruption categorized to a magnitude 8 and powerful enough to wipe out any form of life near it, even other neighboring states in the US. This is why every single activity or change coming from the supervolcano is always observed, and also there are thoughts and theories going on about the Yellowstone volcano because another eruption is thought to be close. Because of this, a body named the Yellowstone Volcano Observatory was formed, and it's dedicated solely to all affairs regarding the supervolcano's activity. This body were also the ones who found out about this rare gas that indicated an imminent eruption of the supervolcano. This rare gas is ancient helium, one that hasn't been seen for a long time, and it's not a good sign. Yellowstone National Park's hot springs, fumaroles, geysers, and other hydrothermal features are known to eject several types of gases from deep within the Earth. These gases include neon, argon, carbon dioxide, steam, methane, and helium. However, the emissions of helium gas are not in abundance when compared to others. Helium can spew out of volcanic rocks that drive hydrothermal activity, but in Yellowstone's case, that is not where most of the helium is detected to be coming from. According to the research done by scientists from the United States Geological Survey, it turns out to be that the park's gas emanates deep in rocks, where it's been kept for hundreds of millions of years before it was even discovered. Aside from the fact that helium is not abundantly present at the Yellowstone caldera, it is the second most abundant element in the entire universe. Helium on Earth can be found in two main forms, but mostly all helium happens as helium-4 because it has 2 protons and 2 neutrons respectively. This type of helium can be produced during the radioactive decay of heavy elements such as uranium. A tiny part, compared to about 1 in a million, occurs as helium-3, which has 2 protons and 1 neutron. The majority of helium-3 has been present on Earth since the planet's inception and is a relic of material that initially formed the planet. The ratio of helium-3 to helium-4, though, somewhat varies, and as a result, scientists can actually utilize that ratio to find out the estimated source of any helium they come across. Other heavy elements like uranium are more conflicting with minerals seen in the Earth's mantle, so these elements filter up to the crust, and in that process, their decay creates helium-4. Mantle materials which possess less of these heavy radioactive elements don't form as much helium-4, so the helium present there is majorly in the form of helium-3. The hydrothermal system at Yellowstone National Park has a pretty high amount of helium-3. And scientists believe this to be proof that the Yellowstone hotspot stems from deep within the mantle and has a relatively straight path leading up. However, it seems that helium-4 has a more complex journey when coming up to the surface. Researchers and scientists from the United States Geological Survey have been gathering gas samples from regions in and around Yellowstone for a period of 10 years. While collecting these samples, they were also performing isotopic analysis of the helium, carbon dioxide, and other forms of gases in those samples. From their research and analysis, scientists discovered that the amount of helium-4 that emanates from Yellowstone is more than the multiple orders of magnitude they would have expected to find elsewhere. The scientists also found out that a huge part of Yellowstone's helium-4 is likely to be at least hundreds of millions of years old, or perhaps even billions of years old. Based on the calculations made by scientists and researchers, combined with the amount of gas present and studied, they concluded that there is a high chance that this gas comes from rocks within a very ancient crust, known to be buried close to the area. This very old pocket of crust, known to be from the Archean eon, which was created over 2.5 billion years ago, contains uranium and other radioactive materials that have been progressively decaying. That probably gave room for high concentrations of helium-4 to build up underground. The scientists then postulated further that possibly about 2 million years ago, the Yellowstone hotspot cut through these ancient rocks and as a result began releasing the helium-4 stored there together with helium-3 brought up from the mantle. Now, you might think that this discovery sounds kind of interesting for anyone intrigued by the wonders of Yellowstone, but for scientists, this discovery comes off as scary because there could be more important implications attached to it. Helium and other noble gases are used to evaluate groundwater residence types. For example, scientists often believe the more helium-4 present in water, the longer that water has been sitting in the rocks surrounding it. However, this research and analysis of the helium at Yellowstone explains now that some of these assumptions, especially helium-4 produced by the steady decay of elements discovered only within the rocks and dregs of the local aquifer, aren't quite correct. Helium can be unpredictable at times. It can unexpectedly come into a system from unexpected places. It could be a pocket of ancient rock or a magma source. So the dates in previous calculations, especially those from aquifers in volcanic areas or near earthquake faults, might be very inaccurate due to the extra helium involved. However, scientists are used to dealing with new information that contradicts and can eventually change long-held theories, because that's the nature of science after all. Regardless, what else can helium tell us about volcanoes? Well, the story about helium emissions related to volcanic activity all started after one of Yellowstone's sizable earthquakes struck, and a shocking event ensued after. People were coming up with their own ideas, throwing around possibilities that animals were running from the park in fear. The earthquake would cause a massive eruption and that helium emissions were rising in the Yellowstone caldera, and it was a sign that an eruption was coming. Unfortunately, these theories were wrong because it wasn't the animals to begin with. They were just migrating. Also, it turned out that helium might be able to give more insights on volcano monitoring in the future. Helium, and particularly the ratio between helium's two naturally occurring isotopes, which are helium-3 and helium-4, can tell us about helium's source. Although helium can come from two main sources, these two sources of helium, however, have several flavors. Mantle-derived primordial helium is dominated by the lighter neutron, while the decay of elements in the crust will produce the heavier neutron, also known as an alpha particle, one of the ways elements decay radioactively. This means that when you examine the isotopic ratio of helium that is released in soils, fumaroles, hot springs, or wells, you can find out the amount of helium is being gotten from either degassing of magma coming from the mantle or from the radioactive decay of uranium and thorium in the crust. If the helium-3 or helium-4 is high, then the mantle source is ruling. If the helium-3 or helium-4 is low, then the crust source is dominating. When we talk about these ratios, normally we compare them to the helium-3 and 4 ratio in the atmosphere, called Ra, which is approximately 0.00001384. So if the helium ratios tend to be reported a multiple of Ra, for mantle sources that is something like 16 Ra, and for more crustal sources it is 1 to 3 Ra. Two recent studies looked at helium emissions in active volcanic areas. The first is looking at the events that led up to the October 12, 2011 eruption at El Hierro in the Canary Islands. A study by Padron and others in geology examined the relationship between helium emissions measured in soils across the island with helium-3 and 4 in water from a well on the island. What they found is that as the earthquakes increased during late summer into early fall, so did the helium emissions across the island, from 9 kilograms per day to over 24 kilograms per day just prior to the eruption. Hand in hand with that, and helium also increased from 2 to 3 Ra to over 8 Ra. Padron and others suggest that the earthquakes helped create fractures for the helium to escape, like a natural fracking process as the magma rose and degassed under the island. However, the crustal helium signature, low Ra, was also overwhelmed by the mantle helium signature, high Ra, from the magma. So the closer the magma got to the surface, the more helium was released and the higher the helium became. After the eruption, the helium emissions decreased with the decreasing seismicity. When seismicity picked back up later on, the helium emissions went back up again, but the helium-3 and helium-4 ratio didn't. Instead, it stayed below 5 Ra, suggesting that the helium was coming from the crust that makes up the island, not mantle-derived magma. The new earthquakes in the northern part of the island created cracks for the helium to escape, but the helium wasn't entirely related to new magma. In fact, helium emissions overall peaked at 38 kilograms per day well after the initial eruption began, while helium-3 and helium-4 peaked with the eruption itself. Overall, the helium emissions seem to track very closely with the amount of seismicity, while the helium-3 and helium-4 tracked with the rising of magma into the crust until eruption. Rising helium-3 and helium-4 related to seismicity has also been noticed at Mammoth Mountain near Long Valley in California, which is interpreted as the evidence that moving magma deep in the crust is driving the earthquake swarms. At Yellowstone, helium tells a different story. A study in Nature by Lowenstern and others examined the voluminous helium that is released within and around the Yellowstone caldera. They found that the most productive areas of helium emissions, like Heart Lake Geyser Basin in the southern margin of the caldera, are actually mainly releasing helium derived from the crust, not any magma underneath Yellowstone. If you look at Yellowstone, the highest helium-3, helium-4 ratios are in the heart of the caldera, with approximately 10 to 17 Ra. It is relatively close to the assumed mantle hotspot composition of almost 220 Ra. At Heart Lake Geyser Basin, the helium-3 and 4 is less than 2.5 Ra, so very strongly controlled by crystal sources. Lowenstern and others calculated how much helium-4 the crust under the Yellowstone supervolcano could produce based on the uranium and thorium content, and found that the Yellowstone area releases almost 600 times more helium-4 than it should based on the decay of uranium and thorium. This means that it is likely released helium that has been trapped in the crust for millions to billions of years, and parts of Yellowstone sit on a crust that is over 3 billion years old. This helium at Yellowstone is in no way related to the magma underneath the caldera, but has likely been freed from the crust by the earthquakes and heating of the crust done by the magma, similar to what happened at El Hierro. You can begin to see the problem we currently have with using helium for volcano monitoring. The amount of helium being released doesn't tell us much, as helium of any gas might be liberated by earthquakes under a volcano. We need to understand the ratio of helium to understand whether the changes in emissions are actually related to magma. So why is that a problem? Well, there isn't an easy way to measure helium-3 and 4 ratios in the field. Instead, samples have to be taken back to a lab to be analyzed, so getting fast helium-3 and 4 ratios isn't possible right now. If you only consider the amount of helium being released at the volcano, you're only getting a piece of the full picture. Imagine you notice a flood going down your street. It could be coming from the downpour that is going on, or it could be from a broken water main up the street. Merely measuring how much water is running into the gutter isn't going to be sufficient to tell you the source. These two studies clearly show that we can learn a lot from measuring helium emissions and their isotopic composition. At El Hierro, it is clear that there is a disconnect at times between the helium emissions and the composition of that helium, while at Yellowstone, there is a significant volume of stored helium in the crust that can be released by processes unrelated to anything that could lead to an eruption. Step by step, we are moving towards being able to better anticipate the action at a volcano, but sometimes you need to be careful not to get carried away without understanding exactly what is happening. Residents of the Yellowstone area, on the other hand, are a bit impatient about their safety following the news about these helium emissions and how it could be a sign of a massive eruption on its way. Well, they might actually begin packing now and looking for safe areas because apart from the helium emissions, scientists discovered that the Yellowstone supervolcano holds more liquid molten rock than they had estimated, and that just seems to be a confirmation about the supervolcano's imminent eruption. The amount of liquid magma rock under a volcano helped scientists and researchers find out how close it might be to erupting, and now scientists have just discovered a similar but jaw-dropping information about the amount of liquid magma under the Yellowstone supervolcano. Magma consists of rocks and crystals at varying stages of solidity. The more melted or liquid the magma is, the more likely a volcano is to erupt. Two large reservoirs full of magma exist beneath the Yellowstone caldera, one that's about 3 to 10 miles beneath the surface and another that's 12 to 30 miles below ground. Based on previous research, scientists thought that the shallower reservoir was mostly solid, with just 5 to 15% melted rock. But after using powerful supercomputers to reanalyze existing seismic data from the past 20 years, they believe that the proportion is actually 16 to 20%. That's still well below the threshold of liquid magma, about 35 to 50%, that scientists believe will trigger an eruption though. While the new findings don't change the volcano's risk level, they do represent a big improvement in our ability to understand what's beneath Yellowstone, says Carrie Cooper, an Earth and planetary scientist at the University of California, Davis, who was not involved in the study. The Earth hasn't created more liquid magma. Instead, scientists say they now have a more accurate understanding of what was already there. It's a bit like getting a new lens on an old camera, says Michael Poland, a research geophysicist and the scientist in charge at the U.S. Geological Survey's at Yellowstone Volcano Observatory, who was not involved in the study either. It's the same camera, but you've got finer resolution now. You see with more clarity. The Yellowstone supervolcano, located in northwestern Wyoming in Yellowstone National Park, is one of the largest volcanoes in the world. It's erupted multiple times over the past 2.1 million years, including 3 massive eruptions that smothered the surrounding landscape in ash. The Yellowstone caldera, which stretches 30 by 45 miles wide, formed during one of those eruptions roughly 631,000 years ago. Seismic waves produced by earthquakes must move through layers of materials inside the Earth before reaching seismometers on the surface. The waves slow down when they reach molten rock, so researchers can use the time it takes them to reach the seismometers to glean insights into how much magma is below ground. Past analyses have assumed that seismic waves emanate linearly from the quake toward the seismometer, but the reality of their journey is much more nuanced than that. This time around, supercomputers modeled the seismic waves in 3 dimensions, which gave scientists a more complete picture of the crystal mush below Yellowstone, as Ross McGuire, a seismologist at the University of Illinois Urbana-Champaign, noted in a statement. This crystal mush detected under Yellowstone defines a lot of events, and at the moment all we can do is wait for more information from our scientists and researchers about these factors that can cause the Yellowstone supervolcano's massive eruption. Do you think Yellowstone could erupt due to the ancient helium detected, or is it not powerful enough? Let us know your thoughts in the comments section below.